This function gives us flounder population. If they want the initial flounder population, all you have to do is plug in 0 in for t. So if you do that, you get 6 in the numerator and 1 in the denominator. So it looks like 6 million. B asks us to determine the slope when there's 10 million flounder per year. So, and millions of flounders. Slope when there's 10 million flounders. So you need to find out the derivative and then plug 10 into it. So the derivative, you could use the quotient rule. So the derivative of the numerator is 7, and the original denominator subtracted by the original numerator times the derivative of the denominator. That's all over the original denominator squared. Okay, that's just doing the quotient rule. And then, yeah, it doesn't look like we have to write it out, so you could just use this and plug in 10 everywhere where you see a t. So I'm going to go to, just reading this left to right, I've got 10 squared. 100 times the 0.2 plus 1 times 7. We got 147 for that first term in the numerator. And plugging in 10 in here. Looks like 304, because 0.4 times 10 gives us 4. Then I plug 10 over here. If I didn't do anything wrong, it should be 304. And that's all over 0.2 t squared. So that means 10 squared times 0.2 plus 1. I think I said it wrong too when I was talking about the derivative. This is at time t equals 10, not when the population is 10 million. So years. How fast is the population changing after a certain amount of years? I don't know if they want it. What do they want? 4 decimal places. It looks like it's negative 7.4762. So it's decreasing 7.4762 million per year by the time we get to the 10th year. Because remember, derivative tells you how fast the population is changing. So the rate in millions of flounders per year, which the flounder population is changing at year 10. That looks like that's the right answer. Average rate of change in millions of flounders per year. It's not the average rate of change. Yeah, I don't know. I mean, that's a tough distinction because obviously the model isn't perfect, but it's not the average rate of change. It's the instantaneous rate of change. So yeah, this looks like this is the best answer. When testing my answer, I found a mistake. This is supposed to be squared with the quotient rule, right? It's the bottom part of the quotient rule is g squared, or the second function squared, the denominator function squared. So that should have been squared over there, which threw off that answer. But everything else is, this is right, and then this is right.